welcome my dear friends and students. In today's video, I am going to explain assumptions of kinetic theory of gases, some basic definitions again, that is the free path, mean velocity, mean square velocity, root mean square velocity, and one very important expression, that is expression for pressure exerted by the gas molecules. Now let us move toward the first point, that is assumptions of kinetic theory of gases. Now these assumptions help us to study, to explain the various properties of the gases, to explain various laws of the gases. So that's why these assumptions are very important. So let us move toward the first assumption, that is gas consists of large number of extremely small particles called as molecules. It means any gas which we consider that consists of large number of particles. These particles are called as the molecules. Then second one, how these gas molecules are? These gas molecules are rigid, perfectly elastic and spherical in shape. That's why second assumption is given, that gas molecules are rigid, means they can regain individually their shape. Then second one, elastic, perfectly elastic and spherical, and perfectly elastic and spherical in shape. Now when we consider the different molecules of the same gas, if we consider oxygen gas or hydrogen gas, when we consider a single gas, and when we consider many gas molecules of the same gas, then they are identical in all respect. Their size, mass, radius, then volume. So that is the concept behind this assumption, that all molecules of same gas are identical. Then next one, these gas molecules are always in state of random motion. It means these gas molecules continuously moves in all possible direction with all possible velocities. So when gas molecule perform motion in different direction with different velocity, that motion is called as random motion. This is similar to that of the Brownian motion. So gas molecules are always in state of random motion. As they move randomly, that's why they collide with each other, as well as they collide with the walls of the container where we consider. These are the gas molecules which collide with each other, or that gas molecules collide with the walls of the container. Now during the collision, they travel along a perfectly straight line with the uniform speed. That's why right here, a molecule travel in a straight line with a uniform speed between two successive collisions. Then next point is time taken. What about the time of impact when they collide with each other? Now the time for which they make contact with each other, that is very small as compared to the total time taken by the gas molecule for two successive collisions. That's why right here time taken for collision is very small as compared to the total time interval between two successive collisions. It means they meet for a very small time during the collision, rather than the time taken by the gas molecule for their two successive collisions. Then, though they are in random motion, but if you count the number of gas molecules per unit volume. On an average, that gas molecules, average gas molecules per unit volume that remain constant. It means some gas molecules moving inside that particular volume. Suppose 5 gas molecules move inside and 3 gas molecules move outside. In next time here that will be 2 move inside and more that will move outside. It means on an average the gas molecules present in particular volume that is always constant. Then what about the force between them? As we know that these gas molecules far away from each other, the distance between gas molecule that is maximum rather than in case of solid and liquid. That's why the force of attraction or repulsion between the gas molecules that is very small, that is negligible. And as these gas molecules are in random motion, therefore this gas molecule possesses the kinetic energy. The kinetic energy of that gas molecule directly proportional to the absolute temperature of the gas. So these are the 10 assumptions on which kinetic theory based. Let us quickly revise it. Any gas consists of large number of extremely small particles called as molecules. These molecules are rigid, perfectly elastic and spherical in shape. All gas molecules of the same gas, they are identical in all respects. The gas molecules are always in state of random motion. During the random motion, they collide with each other as well as they collide with wall of container. During the collision, they travel along a perfectly straight line with the uniform speed. The time taken for the collision is very small as compared to the time interval between two successive collisions. Then the average number of molecules per unit volume of the gas is constant. The intermolecular force of attraction or repulsion between the gas molecule is very small. And last one, the average kinetic energy of the gas molecule is directly proportional to absolute temperature of the gas. Now let us consider some basic definitions. That is, the first one, free path. So in assumptions we already seen that gas molecules are always in state of random motion. So that's why whatever the distance covered by this gas molecule between two successive collisions, that is nothing but the free path. What is free path? The distance covered by the gas molecules between two successive collisions. When we consider these are the two walls of the container, and when gas molecules start from this wall, collide on the next wall and again move back and collide to the other wall. So whatever the distance covered by the gas molecule between two successive collisions, that is called as the free path. Now these gas molecules doesn't consider the same path between the two successive collisions. So that's why we have to consider the average value for that free path. So let us consider the second definition as average free path or mean free path. That is the average of the average distance covered by the gas molecules between two successive collisions. That is called as mean free path. And that mean free path that can be find out by considering the formula total distance covered by the gas molecule between two successive collisions divided by total number of collisions. That is here lambda equal to lambda 1 plus lambda 2 up to dash lambda n upon n, where lambda 1 is the distance covered by the gas molecule between first two collisions. So from that we can easily find out the mean free path. Now this mean free path depend upon which factors. Now here use this formula, lambda proportional to V upon pi d square n, where V is a volume of gas, d is a diameter of molecule, which is called as molecular diameter, and n is the total number of gas molecule. It means this mean free path is directly proportional to volume. This mean free path is inversely proportional to square of molecular diameter. This mean free path is inversely proportional to the number of molecules, that is total number of gas molecules. Here, according to Maxwell, the proportionality constant is taken as 1 upon root 2. That's why I write here lambda equal to 1 upon square root 2 into V upon pi d square n. Now if we have to put the value of n by V equal to P upon kT. Now we have to prove it later on the basis of pressure exerted by gas molecule. So here if we put n by V equal to P upon kT, I write P here, then the quantity kT that will be moved toward the numerator, because it is the here denominator of denominator that goes to the numerator. So lambda equal to kT upon root 2 pi d square into P. Now from that we can here see how this mean free path varies with the Boltzmann constant. K is the Boltzmann constant. How it varies with the temperature, how it varies with the pressure. So these are the general factors with the help of which we can consider how mean free path varies with the different factors. Let us revise again here. When we consider the single gas molecule, whatever the distance covered by that single gas molecule between two successive collisions, that is called as the free path. So that's why right here the distance covered by the gas molecule between two successive collisions, that is called as free path. But when we consider the number of gas molecules, then here the distance covered, average distance covered by these different gas molecules, or we can also consider the same gas molecule but various number of collisions. So here whatever the average distance covered by the gas molecule between two successive collisions, that is called as the mean free path. Suppose in first two collision distance covered is 2 meter, in next two collision distance covered is 3 meter, in next collision suppose distance covered is 2.5 meter, in next collision distance covered is suppose 3.5 meter. Then whatever the average distance covered by the gas molecules between that two successive collisions, then obviously we have to add all these divided by here number of collisions. So that's why I write here total distance covered to the total number of collisions, that is lambda equal to lambda 1 plus lambda 2 up to dash dash lambda n upon n. Now here this mean free path, that is the average of free path, depend upon various factors. So how that mean free path varies with the different factor, how it varies with volume, how it varies with the molecular diameter, how it varies with the total number of gas molecules, how it varies with the Boltzmann constant, with the temperature, with the pressure. So that can be found out by considering this relation lambda proportional to V upon pi d square n, where V is the volume of gas, d molecular diameter, n number of gas molecules. Now if I make some adjustment, that is n by V, if I put n by V equal to P upon kT, then the same thing can be written as lambda equal to kT upon root 2 pi d square into P. Now how this quantity come? It is simply the proportionality constant suggested by Maxwell, that is 1 upon root 2 for this relation. Then we have to consider the next definition, that is the mean velocity. Now we know that gas molecules are always in state of random motion. Random motion means what? That is, these different gas molecule moves with different velocities in different direction. So that's why velocity of gas molecule, that is not same, that is not constant. That's why if we consider C1, C2 up to dash dash Cn be the velocities of n gas molecules. C1 velocity of first gas molecule, C2 velocity of second gas molecule, up to dash dash Cn velocity of n gas molecule. Then we have to take the average, we have to take the mean of the velocities of all gas molecules. So as the name itself indicates its meaning, mean velocity. That is the mean value of velocities of all gas molecules. That's why right here the mean of velocities of all molecules of gas is called mean velocity, and that mean velocity is given by C equal to C1 plus C2 up to dash Cn upon n. Here we are considering C is a velocity of gas molecule. Here in textbook for velocity V is taken, but there is a confusion if we use V for velocity and V for volume. That's why I here use for the speed or for the velocity there is alphabet C. Keep in mind C represent here the velocity of gas molecule. Now mean velocity. Next definition we have to consider as mean square velocity. Now here we have to take now the mean of square velocity. Now the same formula that can be written as for this definition, mean square velocity. It is the mean of square of velocities of n gas molecule, that is called as the mean square velocity. How I define mean square velocity? The mean of square of velocities of all gas molecule, that is called as the mean square velocity, and it is represented by C square equal to C1 square plus C2 square up to dash Cn square by n. Don't be confused here. The formula for mean velocity is C equal to C1 plus C2 up to dash Cn upon n. The formula for mean square velocity is C square equal to C1 square plus C2 square up to dash Cn square divided by n. And if I take the square root of this mean square velocity, then it is called as RMS, that is the root mean square velocity. What is RMS? Root mean square velocity. It is simply the square root of mean square velocity, that is called as the mean square velocity. These are the definitions which are important. What is mean velocity? Simply the mean of velocities of all gas molecules, that is called as mean velocity. What is mean square velocity? The mean of square of velocities of all gas molecules, that is called as mean square velocity. It is given by here C square equal to C1 square plus C2 square up to dash Cn square upon n. And what is the root mean square velocity? The square root of mean square velocity. The square root of mean square velocity, that is called as the root mean square velocity, and it is represented as C RMS. R for root, M for mean, and S for square. A root mean square velocity. The unit for mean velocity, obviously it is meter per second. The unit for mean square velocity is meter square per second square. And here the unit for root mean square velocity is again meter per second. So these are the certain definitions which are very important. That is free path, mean velocity, mean square velocity, and the root mean square